In this lecture, we will discuss the medical physics, the nuclear medicine within the medical physics course, both from therapy and from diagnostics. In fact, you see, this is the definition of nuclear physics, of nuclear medicine. It's a medical specialty involving the application of radioisotopes in diagnostics and therapy. Radionuclides can be injected intravenously or inhaled, depending on the substance, and they concentrate in the organ to study or treat. Imaging is always done by detection of gamma rays emitted from the patient's body. For this reason, it's also called endoradiology. Okay, so it's radiology from inside. Because the information is not on the anatomy, but on the function, which depends on the molecule selected to carry the radioisotopes. It is also called physiological imaging, functional imaging, or molecular imaging. So it's gives you more information than conventional radiology, because now you can select an isotopes, and so you have a functional, physiological information too. From the therapy point of view, this is called targeted radionuclide therapy. And here you have to find a binding between a radioisotope and the molecule, which is targeting cancer cells as specifically as possible. This compound is called the radiopharmaceutical. Generally, radionuclides are, for many years, were essentially beta emitters. But these days, you also have more and more alpha emitters in the market that are very difficult to produce. We will discuss it. Some radionuclides or specific combination with similar chemistry can be used for simultaneous imaging and therapy, and this is called theranostics. So the decay, of course, you know already the basic radioactivity. This is only as a reminder, let's say, that because we will see a little bit different state. This is a generalized decay scheme. Generally, what happens is that when you have a given compound here, AZX, you can have electron capture decay or beta decay, and beta plus decay goes into this compound. On the other hand, if you go into beta minus decay, you go into an AZ+1 excited state, and from these excited states, you have an isomeric transition in a gamma. So very often you will see beta minus associated to gamma decay. And of course, the activity, as you know, goes down exponentially, and you can define the half-life of the compound. Now, this is a list, a very interesting list of radionuclides used in nuclear medicine. It's not exhaustive, but you will see, I mean, it's almost exhaustive. I mean, and you see the applications. Most of them are for imaging. Some of them are for therapy or just for research, like in vitro assays. You see that in most cases, you exploit beta decay, other beta plus decay. These are all beta plus emitters for imaging, for PET. We will see positron emission tomography. Beta minus. In some cases, you exploit instead electron capture, like for gallium, for indium, for iodine, not for iodine 131, which is one of the most used for thyroid imaging. And these are this is not including the alpha emitting that are used only for therapy, of course. So this gives you an idea of the half-life, and this gives you an idea of the energy which is emitted in correspondence with these transitions. Now, if you look at the use, let's say now the name of the isotopes, this is the isotope chart, okay? The usual isotope chart as displayed is the the charge, the number of protons and the total number of neutrons plus protons. If you look at the chart, and you look at SPECT, PET and therapy are in different colors. SPECT is the single photon emission computerized tomography, so it's the imaging by gamma rays. PET is the imaging that use positrons. In reality, use gammas emitted by positron annihilation, but is always positrons. And therapy are in blue. The sides of the name of the isotope here is proportional to the use in the nuclear medicine community. So you see that there is a lot of technetium 99 metastable. This is 99M technetium is by far the most used, but also with a lot of use is iodine 131. This is for therapy, but also for imaging, for the thyroid. And there is also a lot of fluoride 18, which is used for PET. It's very useful for diagnostics in PET because it can be bound to glucose, and so it identifies the areas of the body where glucose is particularly used. And since tumors use a lot of sugar, this is a very sensitive probe for tumor. But there is also a few others like lutetium 177. We will see this is now the most used isotopes for therapy, apart from iodine 131. This is a beta minus emitter and is very much used. So let's see why. Let's start with the production methods. Production methods are, you see, there are very different ways. You can have cyclotrons, so accelerators. You can use a nuclear reactor. You can use either using fission or using neutron activation, or you can use what is called a radionuclide generation, where essentially it's a natural way to produce it because you use the decay of the parent. You load the radionuclide generation with the parent radionuclide, and then you look at the decays and you collect the daughter radionuclides that you need. You see here there is a different characteristic. I mean, the bombarding particle, which is of course not existing in the radionuclide generation, but in cyclotron you typically use protons, deuterons, tritons, or helium ions, and neutrons, of course, in the nuclear reactor. The product, the type of decay, the typical carrier-free, if it is typically carrier-free, the high specific activity, and the relative cost. Of course, this is more expensive. And these are the examples, let's say, how the typical products. At cyclotrons, you see, you typically produce this type of isotopes, including 18 fluoride that we have seen is very much used. In nuclear reactors, you produce these products, including 99 molybdenum, which is very important because it's the parent of the 99M technetium. And in the radionuclide generator, you produce typically these, including this famous technetium, which is the most used, as I told you. So what is the difference between reactors and accelerators? So the major drawbacks, let's say, in using a reactor is that you produce a lot of radioactive waste, and you produce a lot of radioisotopes which are not really required. So you have to isolate what you need, essentially. For accelerator, of course, you have a lot of advantages, you see listed here, but the major drawback in some case, an enriched target material must be used, and as target, and this can be very expensive. You have to produce special targets with enriched isotopes, and then you have to throw it away, so that you have to produce another one. So the essential steps in radionuclide production are shown here. The acceleration of charged particles, beam transport, irradiation of the target, nuclear reaction producing the target, which is typically written in this way, you know, the usual way, target processing and material recovering, labeling of radiopharmaceuticals, and quality control. These last steps are extremely important for the quality control. Let's say what is called GMP lab, good manufacturing practice lab. At the end, you produce a vial which must be used in the clinics. So it has to be certified somehow. You see typically a typical nuclear reaction in a reactor, in an accelerator. Now, very important is this quantity, is the production rate. So it's essentially, this gives you the number of nuclei of the compound you want formed per second. And it can be shown, so it's the N over the T. And this number of nuclei formed per second can be expressed by this formula, where you see N is the target thickness in nuclei per square centimeter. I is the flux, is the intensity, so the incident particle flux per second. Lambda is the decay constant, typically. And then you have an integral, and the integral is the integral of the cross-section, of the reaction cross-section that, of course, you have to know, divided by the energy loss per unit track, the LET of the beam, if you want. And this is integrated from the initial energy to the final energy of the incidence particle along the path. So you do the integral of the cross-section divided by the LET in this region. And then this way you come out with the production rate of the particle. Okay? So the cross-section is of course, is the most important part here in this formula, and it is energy dependent, of course, and very often has particular resonance energies. You see, this is the example. For example, this is the reaction that leads to the formation of fluoride, starting from oxygen 18 target irradiated with protons. So you irradiate a special target in oxygen 18, not oxygen 16, and oxygen 18 plus protons gives neutron and fluoride. That is what you want. And you see that if you look as a function of the energy, there are regions where you have resonance here at low energy, like at around 5 MeV. Here you see 7 MeV, there is another one. The other important factor in the formula for the calculation of the reaction rate is the saturation factor, which is 1 minus E2 minus lambda T. So, of course, the practical production limits of a given radionuclide are determined by the half-life of the isotopes. So the problem is that, of course, if you want fluoride 18, the half-life is about 2 hours. But if you want oxygen 15, the half-life is about 2 minutes. So this means that if you want to use oxygen 15 as a radionuclide, you have to be able to deliver it in minutes to the patients. While if you want to use fluoride 18, you can still imagine that you can quickly isolate the fluoride 18 and transport it. So for long-lived species, where you don't have to worry about this factor, the production rates are usually expressed in terms of the integrated dose or total beam flux. So in microampere per hour, because here you don't worry about the decay. So typically you see the cyclotrons that you use, depending on the energy of the cyclotrons. This is a small low energy 18 MeV ACSI cyclotron. There are different companies producing these low energy cyclotrons. For high energy cyclotrons, one of the main retailer is IBA, a Belgian company that also produces cyclotrons for proton therapy. And you see that from 0 to 10 MeV, you produce the famous fluoride 18. I would say that most of the cyclotrons this day go in for sale are in this, either in this region, because you can also produce other isotopes, or up to 30 MeV, where you can produce many, many isotopes. If you go higher than 30 MeV, like 70 MeV is a typical value we will see, like the Aronnax in France, you can produce much more. You see here a long list of radioisotopes that you can produce. But of course, the cost is much higher. Aronnax is the example I wanted to give you, because this is one of the most important centers for radionuclide production in Europe. It's a high energy cyclotron, 70 MeV, it's an IBA machine, and high intensity. You have 750 microamperes of protons, and this will produce a large variety of radionuclides on a regular schedule and in sufficient amount to perform clinical trials. You see, it's a very established system where you can extract the radionuclides, and you have a GMP radiochemistry lab. This is one of the few centers where you can get lutetium 177 that I described you before, but there are also other copper isotopes that are also very important. So the other systems, I mean, when you have for radioactive beams, you can separate radioisotopes with two systems. I mean, one is called the ISOL, the isotope separation online, and one is called in-flight. So for the ISOL, you start with the accelerator, and you have a thick target. Now, this means that all your elements are formed in this thick target. At this point, what do? You heat up the target, and then you use the heated up target as a new ion source for the accelerator, where you can now re-accelerate the particle, but using magnetic deflection, you can select the target that you want, and then you can now accumulate the rare isotopes that you really need. So you see that the advantage that you have is that you have an excellent beam quality. The disadvantage is that you have to develop a diffusion process for each element. In flight is much simpler. It's what we do with GSI, for example, where essentially you shoot the stable beam on a target, and then you do the selection in flight. So now you have a beam of rare isotopes here. Of course, the advantage is that you have no chemical process involved. You can have high intensity beams, but the disadvantage is that it's a very expensive system, because you need a very intense primary source, and you need a complicated accelerator. So there are a few, in addition to GSI, few accelerators that do this work. While for ISOL, the most famous is certainly ISOLDE in CERN, which is very much used for that, but also Spiral 2 in France and SPES in Italy. Another example of ISOL, which is now under development, is FRIB in United States. In this case, though, they don't make a re-acceleration. They have a primary beam. You go through the target, and you block your unused primary beam here. So you produce your isotopes here, and from here you do the harvesting using chemical purification. This is now in the new center in FRIB in Michigan State University. Finally, the radionuclide generator, that, as I say, they are very cheap compared to the accelerators. And you see that you can produce from parents like germanium, rubidium, strontium, and the famous molybdenum, using different decay, you can get different daughters like technetium-99. And then, of course, the decay of these daughters goes into final products that are generally stable. So you want this, this daughter here. This is how it looks like. Essentially, you have to load your generator with your parent, and then you have to elute in columns the daughter that you need. And you have to do it quite quickly because, of course, you don't want to have a lot of redecay. This brings to what is called the transient equilibrium. You see, between elutions, the daughter builds up. In this case, you see, is 99 technetium. Build up as the parent molybdenum continues to decay. So this is now, this is the activity, this is the time. You see, the decay of 99 molybdenum is constant, you see. So you have an increase of 99 technetium. Then after approximately 23 hours, the 99 technetium activities reach a maximum. Because you see, at which time the production rate and the decay rate are equal. And the parent and daughter are said to be in transient equilibrium. Once transient equilibrium has been reached, the daughter activity decreases with an apparent half-life equal to the half-life of the parent. So what you have to do here, instead of decaying, you make your elution at this time, at 24 hours, and then you will have another cycle. So you can elute many times until the 99 molybdenum is gone, and you can collect a lot of 99 M technetium. Now, once I do the production, what do we want to do with these isotopes? For imaging, there are essentially two techniques, the SPECT and the PET. SPECT, let's start to see them. The pattern is always the same. You know, you give a radiopharmaceutical, the radiopharmaceutical concentrate in the desired location. The nucleus of the radionuclide decays to emit gamma rays, typically for imaging. And then you have to detect the photons using what is generally called the gamma camera. This is more for SPECT. For PET, we will see it a little bit different. So the gamma camera is pretty simple. You see, you have, this is your patient where you have now you have injected the radioisotopes accumulated in some regions shown here. And then you go through a collimator. That's very important. The collimator is something special in the gamma cameras. And then you have detector, then you have photomultipliers, preamplifier. This is the usual electronic chain, you know, amplifying sum, pulsate analysis, position analysis, and then you will see the image on your computer. The collimators, as I told you before, are extremely important in SPECT. You can see why here, you see, because if this is the source, if you have a detector, you will lose all the information on the position if you don't have the right collimator. So you see, using a collimator, you actually select the position of the beam. It's also shown here, and this is a parallel hole collimator, which is generally used in SPECT. What is the physics here? So the intensity of the signal is proportional to the number of gamma, and this can be given by this formula, where epsilon is the so-called detector efficiency, and omega is the solid angle. In SPECT, the intensity and the resolution of the gamma signal degrades with increasing depth due to the attenuation through the body tissue of increasing thickness. So that's why you have these terms, E2 minus integral of mu x and x, because you can have different attenuation coefficients along the path. You know, you go through the bone, through the fat, through the muscle, and so on. In addition, you have the degradation of collimator resolution with increasing source collimator distance. So essentially, you lose the the collimation, because you will always have a cone, and then this cone is worst. So easily you can show that this the collimator resolution is given by this formula, d times L plus Z divided by L. Having constant hole diameter d and a hole length L, and Z is the depth between the collimator and the point. So the other point is the spectral penetration. You see, this is the spectrum of technetium-99. You see, this is the energy and this is the relative number of counts. So you have a large photo peak at 662 kV. And then, of course, you have a lot of residuals here corresponding to the Compton edge, to the backscatterer peak, and to the X-ray emission specific from different targets. You know. So you don't want to have energy loss, like in this case. You want to stay in a situation where all the energy is absorbed. How is the images now looking like? I mean, generally, that's how it looks like a SPECT machine now. So most cameras use rectangular heads and are designed for SPECT imaging. The dual head is the most common design, so that you have tomographic images that can be produced by acquiring conventional gamma camera, which is 2D, at several angles around the patient. So you end up with 3D images. This is a whole body SPECT of a patient in anterior. The way to do it is the so-called sinogram. So you use a rotation where you detect the signal at different angles, and then you do a back projection of profile at 0 degree. That's an example for 2 angles. You will have the interference here. And then you can do a back projection in 8 angles, and then this is with 256 angles, and eventually you reconstruct a voxel. The procedure goes through iterative reconstruction and can model various corrections, you know, the collimator, the scatter, the system geometry, and the detector resolution. And that's eventually how the image in 3D now looks like. This is a SPECT CT, so you can actually overlap your SPECT signal to the CT image. And eventually what you see here, this is PSMA SPECT CT imaging, indicating a lymph node metastasis near the left iliac blood vessel. So you see, this is how it looks like in the CT, and this is how it looks like in the PET CT. So you clearly see here the signal, and this is the whole body SPECT image where there is a point here. Of course, you see also a lot of accumulation in the bladder, in the kidneys, and here in the region of the axillary lymph nodes. Now, why 99 technetium is so much used? One of the main reasons is that 99 technetium is used in cardiology. It's used in cardiology in the form of sestamib or tetrofosmin radiopharmaceutical. They attach to the cells of the myocardium, so to the heart muscle. They are specific. And this allows you to have an image of the heart, which is generally shown in these images here in 3 lines of images. It's also dynamic, of course. You have the short axis, top to bottom, the long axis, which is the vertical axis. This is side to side, and the horizontal long axis, front to back. So you get this kind of images from myocardial perfusion. This is the SPECT machine that you have to use for that. Why this is so important? Because that's what you use to look at the stress test. You see, this is in rest, and this is in stress. So you see the difference between this signal and this signal, this signal and this signal. And you know, in normal subjects, you see this is a stress test, in normal subject, how the response should be. If you have an abnormal stress test, that's how it will look like. And this is and then you have a warning, let's say. So out of this myocardial perfusion, you see that most of them happens in the United States. United States is one of the main centers where they use this technique. You see, there are in 2007 there were 8.5 million myocardial perfusion SPECT procedures reimbursed in the United States. 8.5 million. And in Europe, this heart with the technetium takes about 25%, so it's about 1/4 of all the nuclear medicine procedures in Europe. There are also other applications of 99 technetium beyond the applications in cardiology. These expand, for example, to brain. That's a nice example. This drug is HMPAO, is a drug that you can bind with technetium, and this molecule is unstable and converts rapidly from lipophilic form, which passes the blood-brain barrier, into a hydrophilic form, which is unable to pass it and is trapped in the brain. And so this gives you, this stays in the brain and gives you an image where you can associate the image to specific pathologic conditions like Alzheimer's disease or depression, this pathological depression. Now, the other large imaging system instead is PET, positron emission tomography. Here, the principle is completely different here. I mean, it's not completely different because eventually you still look at gamma rays, but you look at gamma rays not from the radioisotope itself, but from the recombination of the beta plus emitted with the electron. What is the advantage here? The advantage is that now you don't have one gamma ray per radioisotope emitting, you have two, because every time you have a recombination of a positron and an electron, you produce two photons that are emitted at 180 degrees. So clearly, you see, the idea is this one. The idea is that if I can look with two detectors at the coincidence of the two gamma rays, I can then reconstruct the path and identify the point with greater accuracy that I can do with the SPECT. And moreover, of course, if I rotate around the patient, I can build a 3D image. So, of course, I need a positron emitting. The typical isotopes used are this one with the large majority is 18 fluoride. There is some problem related to the range in tissue of the positron. You see, if you use gallium-68, you have a high energy, so it's a longer range, which declines make a problem, let's say, in the resolution of the image. So you see that the resolution can be in the order of 1 millimeter. If you go to high energy, you go in the order of 2 millimeters. This is the formula for the intensity, which will be given, is essentially proportional again to the absorption. So if T is the thickness of the body along the line and D the depth of the event, the intensity for the annihilation signal along the line becomes independent of the depth. So the intensity of the coincidence is the intensity of the true, plus, of course, the intensity of the random coincidence that are not associated with beta decay. And so you can write it in this way, where epsilon is the detector efficiency and omega is the solid angle. This is the intensity of the random coincidence, is given here. And then the ratio, you see, in the intensity of the true divided the intensity of the random is 1 over I0 times tau, which is independent of the efficiency and solid angle, but only depends on the intensity of the emitted annihilation radiation, I0, and the coincidence time window. So the tau is very important, and tau is in the order of 10 to minus 6 seconds. So it's in the order of microseconds. That's the window where you actually collect and process these coincidence events. Okay, there are ways, you know, to improve this resolution using electronics, essentially. By decreasing tau, of course, you get a better signal. Then the separation is based on the fact that the random events come continuously, while true events come within a few nanoseconds. You know, so you can use electronics to separate them, and then you get a better resolution. Now, these are modern PET signals that generally use a ring of individuals, small sodium iodine scintillators detectors. Each detector is coupled to his own photomultiplier tube. You see, you have the crystal and you have the photomultiplier tube. So you need a lot of detectors. It's going to be expensive, of course. Each detector is coupled to his own individual phototube, and it's electronic coincidence with any of those detectors at the opposite side of the patient. But the advantage is that with such a device, a multiple imaging can be obtained in one shot. And this is particularly important if you want to monitor physiological process with short time scales. That's how it looks like then, the PET scanner. You see, you will have this ring of multiple detectors. What you see here is actually a PET-CT, which is probably the most common these days. So you get, so you can automatically overlap your PET image on the anatomical information. You always need, in functional imaging, you will always need the anatomical information. So eventually you always overlay your functional imaging with the anatomic image. These rings now are up to 23,000 detectors, and they have an axial coverage now of up to 26 centimeters. They must have good stopping power. They must be fast for accurate coincidence measurements. And these days, normally you use the LISO together with the BGO scintillator. So you see the typical PET detectors have high stopping power, light output, and short decay time. And you see here the comparison of LISO, BGO, GSO, and sodium iodine in terms of density, of absorption coefficient, decay time, relative light output, and energy resolution. Now, of course, if you compare the SPECT versus the PET, the large advantage is for the SPECT. You have to rotate the camera head around the patient, but for PET, having a ring, you have a simultaneous acquisition. And as I told you, eventually you do this PET-CT image fusion with results that are really spectacular. You see here, this is an example of PET. As I told you, the 18 fluoride combined with deoxyglucose is by far the most used PET radioisotope. This is called 18-FDG. Why? Because, as I told you many times, cancer cells use a lot of sugar, and so using the aerobic glycolysis, so using 18-FDG, you can easily find tumors, and that's a nice example here. You see very clear image here. Forget about the bladder here. Just look at the tumor. Here you see clearly where is the tumor overlaid with the anatomical description. It's a lung tumor. You can also get now this beautiful whole body PET CT scans. Look at how nice is this image. This is a very recent image. It's not a cancer. It shows glucose metabolism all over the body with an 18 FDG probe. This is very recent one from University of California, Davis. It's called the Explorer PET CT. And is a whole body. So you see everywhere the use of glucose. You see the brain is one of the main users, you see, of our glucose, but you also see that you need it for the heart. And then, of course, you have the kidney and the bladder where it goes down. And this is the difference you see between scintigraphy, so the 2D imaging, SPECT, where you have this rotation, and PET. This is a patient with multiple metastases. You see that actually if you use normal scintigraphy, you will have a hard time to find these multiple metastases. You do pretty good with SPECT already, but the resolution is absolutely fantastic when you switch to PET. You can also do something different. This is something, is a very recent paper from 2019 from the University of Heidelberg, where they're using something different from the 18 FDG, which is, as I said, is the standard. They're using something different. This is gallium-68. We have seen gallium-68 among the candidates for PET. But is bound to FAPI. FAPI is the fibroblast activation protein inhibitor, FAPI. And this is a target for cancer-associated fibroblasts. So it's not really targeting the cancer cells, but it's targeting the fibroblasts that are part of the tissue where the cancer cells grow. I think it's a very interesting approach because this is independent on how the tumor burn glucose, so on how actively they move into the metabolism. And you see that it works pretty well for many different kind of tumors. You know, you have sarcoma, esophageal cancer, breast cancer, lung cancer, colorectal cancer. It's a very interesting systems, you know, to do PET, developed here in Heidelberg and close to us. Now, we discussed before the myocardial perfusion, and we say that it is normally done with the 99M technetium. But of course, you can also do it with SPECT. In this case, you don't use technetium, you use rubidium-82, and you see the difference, stress test using the SPECT and using the PET. This is the ratio of the images with the rubidium. No, this is only for rubidium, stress versus rest, that gives you the information on the power. So if you look at diagnostic accuracy for sensitivity, specificity, and accuracy, you remember sensitivity and specificity we saw in the previous lecture, the meaning is for the false positive and false negative, essentially. You see that the PET is always doing a little bit better than SPECT. So you can argue, why don't we use PET? Why don't we forget about technetium and switch to PET for myocardial perfusion studies? Well, the main reason is the production of rubidium-82. You see, for rubidium-82, you generally use generators, radionuclide generators, starting from the parent, which is strontium-82. But to do strontium-82, you have to start from rubidium-85. And to do that, you have to use this reaction, you see, which is, this is the reaction that produces the strontium from the rubidium using protons. And this the cross-section has a very short peak at 50 MeV. So this means that you need relatively high energy protons. relatively high energy proton, because as I told you, the large majority of protons of cyclotron for radionuclide production are up to 30 MeV. For many years was no more than 18 MeV. Now it's up to 30 MeV. So there are only few places where you can do this. You see, these are Brookhaven in US, Los Alamos in Russia, Triumph in Canada, Itemba in South Africa, Aronnax in France, and Zevacor in US. Not many places. You know, you need the current, you need currents in the order of the microamperes if you want to achieve these results. Okay, now let's move to the problem of the target radionuclide therapy. Target radionuclide therapy instead, not imaging, but therapy. Essentially here we will talk about metastatic patients. We don't, the rationale for using radionuclide therapy is not solid tumors where teletherapy, as we have seen, or even brachytherapy work very well. But when you have these kind of patients, as we have discussed many times, you need immunotherapy, and radionuclide therapy is somehow a kind of immunotherapy. We will see why. It used the so-called Troy horse principle. So essentially, you want a Troy horse that enters in the tumor and then destroy the tumor from inside. You need a lot of conditions to make it work. You need the attractive vector, so you need the high uptake by the target and not by the normal tissue. Must be transportable, good in vivo stabilities. The warriors, so let's say that must be not visible to the cancer to make sure that they don't destroy it. You have to be careful with the half-life, of course, and with the activity, and it has to be specific. So it's not easy. But the basic idea is all here. So what you do, you have your radionuclide, which eventually will be the killer. Then you need the linker. Then you need, that's the most important part, is the part that will bring the radionuclide to your target receptor. And generally, you have to use a peptide, an antibody, or something different, and this will be the one that will bring your radionuclide specifically to the cancer cell. There are not many examples, of course. Not many examples because it's very difficult to be specific, to target specifically. One good example is the so-called dotatate. This compound here. This is a compound containing tyrosine octreottate, which is a somatostatin receptor agonist. And in addition, this is the tate, there is the bifunctional chelator DOTA, which is tetraxetan. Now, somatostatin is interesting because generally receptors of somatostatin, so this receptor, are not very common in normal cells, but are very high densities in different cancers, like CNS, breast, lung, and lymphomas. So these compounds is interesting because you see, if you use this compound, you will bind to the somatostatin receptor and you have a high probability to target cancer cells. Then if you have a good killer here, you will kill the cell. What are the most common applications? You see, the most common applications at the moment go with the three kind of tumors: non-Hodgkin's lymphoma, where you use yttrium-90, and you use the CD20 as a receptor because this is a receptor of stem cells. Neuroblastoma, where you can use iodine and a neurotransmitter because the neuroblastoma have these receptors for neurotransmitters. And then you have the palliation of bone metastasis. These are molecules that target the metastasis. They are generally palliative because you will need a dose which is too high to kill them, but this is very much used. And all of these molecules here are beta minus emission. So most of the applications of radionuclide therapy these days is done with electrons with the emissions of betas. When you use DOTA-TATA, you can combine with lutetium 177, and these are examples of results. This is a clinical trial with lutetium 177. These are survival curves of the patients. We will see more in medical statistics about that. You see that the patients using the lutetium as compared to the patients using only the placebo have a much better survival. This is also an example of lutetium 177 used for treating prostate cancer now. So this is a patient, you see a patient which is metastatic, highly metastatic. So this is a patient that generally has no hopes, but then he had 3 injections of lutetium 177 at the distance of 1 week each other, and that's what happens at the end. You see, all the metastases are gone. So you really were able with PSMA to target the receptor in the metastatic prostate cancer and to kill all the metastases. So not surprisingly, you see this is the number of papers on lutetium PSMA as a function of the years. You know, after this paper that was in 2015, you had something like 30, 40 papers per year, because a lot of people are working now on this system. You see, there's a number of papers now. So lutetium 177 is becoming maybe the most important compound for radionuclide therapy. This is the decay scheme. You see, it's a beta decay that decays on different energy states of the daughter. And the lutetium production process are based on irradiation of isotopically enriched lutetium 176 or yttrium 176 with reactor neutrons, followed by radiochemical processing of the irradiated target. So the production of lutetium is done at reactors, and then you have to carry, you see here, your, this is a funny car tag, you have to carry it to the hospital. So why instead of beta we don't use alpha? Clearly there is an advantage. No, the advantage is that while beta have characteristically, they have long ranges, so they end up to irradiate also the normal cells with high probability. Alpha particles have a very limited range and they have a very high RBE. So even while 1 electron will not be enough to kill a cell, 1 alpha particle is very likely to kill a cell. So every time you have a binding of 1 single molecule, you can kill that cell. Not 100% sure, but high probability. So this is called TART, targeted alpha radiation therapy. And these are typical elements that are used, typical radioisotopes that are used for it. What are the limits here? The main limit is the production of radionuclides. So now it's not so easy to produce these heavy elements that you need for targeted radiotherapy. The other problem is the handling of recoils. So what happens essentially that when you have the decay of the alpha particle here, what will happen, for example, or here, I mean, what will happen, you produce a short range alpha particle, fine, but then you will have the recoil that will now be free because the binding energy is such that you produce a recoil that now goes free. This is generally also radioactive, and so it will go to irradiate some normal tissue somewhere. But the results are really spectacular. You see here, we have another case of metastatic prostate patient the image that you see are all obtained with the gallium-68 PET-CT. And you see that after treatment 2 times with lutetium-177, there was no improvement. In fact, there was progression. You see that the PSA even increased from 294 to 419. So this means that the tumor is progressing. But after 2 applications of actinium-225, which is an alpha emitter, you have this situation, and with 1 more, you have now this situation in PET SPECT, and the PSA drops to normal. This is an amazing result that shows how the alpha particle therapy can work in those patients where targeted radiotherapy with beta emitters does not work. There is another idea, though. You know, the alpha particle have a short emission, so you never use it in brachytherapy because it's too short. You will not have enough irradiation. You see, this is the typical brachytherapy for an ovarian cancer. You know, where you see the distribution here of the needles. I'm sorry, no, this is a prostate. This is a prostate cancer where you put the needle and then you have the distribution of the needles. Then you will have beta emissions and hopefully you cover enough of the tumor. Can you do alpha particle brachytherapy? Well, the idea of the alpha particle brachytherapy, as I said, you cannot do it in principle because the range is too short. So you will need 1 needle per each cell. But if you take a chain of decay where it goes into a gas that can diffuse in the tumor, like happens here if you use thorium and which decays in radium, then you can find a solution. This is, for example, if you use radium-224, this decays alpha in radon-220, which is a gas, is diffusing, and this is alpha decay into polonium-210. So if you go on this, which is immediately decaying again with alpha in the stable lead. So if you use these elements here, you can do brachytherapy with alpha particle emitters, which is now there is a company called Alpha Tau in Israel, which is doing it. And you see, it's very interesting. This is an example of brachytherapy, let's say, using this is, of course, it's in animal models, but now there are clinical trials in humans. You see the dose distribution here, which is diffusing from the very high dose in the center, and then you have another region also relatively high dose, and then you have live cells in the border where the dose is now dropping. The problem, as I said, is the production. One of the few places where you can produce these radioactive isotopes again is Aronnax in France, where actually you use helium-ion bombardment of bismuth-209 at an energy of about 28-29 MeV alpha beams to produce this astatine-211. The astatine-211 is the one that you have used, that you have seen in the prostate stage 4 patient before. Finally, there is another idea that you can have for theranostics. That is to say, okay, what if I use, if I produce the same, if I use different isotopes of the same element, so with the same chemistry, so I can bound them to the same, but I have different properties. So I can use it both for imaging and therapy. The most spectacular case is probably the terbium, because terbium has 4 isotopes. One is gamma emitter, one is beta plus emitter, one is beta minus emitter, and one is alpha emitter. So if you use terbium, but this also applies to other, you see, but terbium is particularly nice, you can have SPECT, PET, beta therapy and alpha therapy with the same chemistry, binding these different isotopes to the same carrier. This is what they are doing at Isolde at CERN, where they are working hard in the production of these terbium isotopes with the ISOL method. And with this, I'd like to conclude. Thank you very much. And in the next lecture, we will touch on medical statistics.